Hi guys, welcome to the very first method in machine learning section. In this lecture, we are going to talk about linear regression, which is a very simple approach and also considered the workhorse for supervised machine learning. Linear regression has been around for a long time and is the topic for countless textbooks. It is very useful and widely used statistical or machine learning method. Moreover, it serves as a good jumping off point for new approaches. It's always a good idea to know the history of something we are going to learn about. I hope many of you are already familiar with method of least squares, which was published by Legendre in 1805 and later on by Gauss in 1809. However, the term regression was first coined by Sir Francis Galton in his published work in 1875. He was actually describing the biological phenomena for relating the heights of descendants to their tall ancestors. For him, regression had only the biological meaning, but his work was later on extended by his students to more general statistical context. In his study, Galton discovered that a man's son tends to be roughly as tall as his father, but the son's height tends to be closer or regress or drift towards the overall average height. It would be much easier if we take a simple example to understand the linear regression. The simplest possible example with 2 points is shown in the diagram. If we draw a line which is closer to each point as much as possible, the line will be exactly through the point. Simply, to fit a line using least square method, we only measure the closeness in the up and down directions. What if we have more than 2 points or we want to add 2 or 3 more points in the same dataset? Let's see how it works. Now, we have 2 other points, C and D. If we draw a line following the same rule of least square method, the line will be different from the given points. It may not pass through the data points. Now the questions are, is the black line best fit line for the given data points? If yes, why this one is the best fit to the data points? Let's explore a little more to learn about the best fitted line. If we follow the standard approach, the best fit in the least square sense minimizes the sum of squared residuals. Residuals are the difference between the observed values and the fitted values provided by the model. In very simple words, to get the best fitted line in the linear regression, we attempt to minimize the vertical distance between all the data points and their distance to the fitted line. The distances from the data points to the fitted line are shown by a double arrowed line in the red color. So let's look at the Galton's data once again. In the plot shown, the blue data points are actually the heights of the fathers along x-axis, whereas the heights of the sons along y-axis. We have a black line which is actually the fitted regression line using least square model. With this data from multiple men and their sons' heights, if we know the height of a man, in principle we should be able to predict the height of his son even the son is not born yet. And this is the idea behind supervised learning. We have a bunch of labeled data points to create the model. Once we have created the model, we can deploy that model on unlabeled data for future predictions. Like we can find out the height of the sun even the sun is not born yet. So before we move on to the notebook for hands-on training, let's discuss few very important and fundamental concepts in machine learning. The very first thing I want to discuss here is no free lunch theorem. As we know, much of machine learning is concerned with devising different models and different algorithms to fit them. For any particular dataset, one specific model may work best, but some other methods may work better on a similar but different dataset. So there is no universally best model. This is sometimes called the no free lunch theorem. And the reason for this is that a set of assumptions that work well in one domain may not work well in another domain. As a consequence of the no free lunch theorem, we need to develop many different types of models to cover the wide variety of data that occurs in the real life. So for each model, there may be many different algorithms we can use to train the model, which make different speed, accuracy, complexity trade-offs. In such trade-offs, one of the very important and fundamental concepts involves bias and variance. So as we move on in machine learning section, we will explore further to widen our concept on types of models, their selection and evaluation. At this stage, let's discuss one of the fundamental concepts in the model performance, which is bias variance trade-off. This has great importance while working with real-world data. So let's see what is bias and what is variance. What are their fundamental definitions? Bias is an error from numerous assumptions in the learning algorithm. High bias can cause an algorithm to miss the relevant relations between features and the target outputs. This is also called underfitting. Let's talk about variance now. Variance is an error from sensitivity to small fluctuations in the training set. High variance can cause an algorithm to model the random noise in the training data rather than intended outputs. Graphical visualizations are always helpful. Let's try to understand the concept of bias and variance with some graphical visualization using bull's eye diagram. In the given diagram on our right side on boards 2 and 4, we can see the data points are scattered, so they do have high variance. On the left side, if we notice the data points are all together, so they do have low variance. If we move from top to the bottom, 1, 2, and 3, 4, we see low bias and high bias in the boards. Consider the center of the target is a model that perfectly predicts the correct values. Moving away from the bull's eye, the predictions get worse and worse. So we can repeat our entire model building process to get a number of separate hits on the target. Each hit represents an individual realization of our model, given the chance variability in the training data we gather. If we have good distribution in our training data, the model predicts very well and close to the bull's eye. On the other hand, if our training data is full of outliers or non-standard values, this results in poor predictions. These different realizations result in a scatter of hits on the target. Here comes the bias and variance trade-off. Let's have a little deeper look on this plot. On the board 1, we have low bias and low variance. If we see our predictions, all the points are somewhere at the red spot. So we can say our model is performing very good. On the other hand, if we look at board 2, where we have low bias and high variance, the predicted values around the bull's eye with high degree of variance. If we look at board 3, where we have high bias and low variance, our predictions would be highly biased at a certain location, and they will have very low variance. We can see all the data points are all together. On board 4, where we have high bias and high variance, we have predictions all over the board. It's very common practice for the beginners to fit the training set very well. So the learners actually add more complexity in the model so that the line fit pass through all data points. This will lead to the wrong predictions of the dataset, which is unseen by the model, called overfitting of the training data. Let's try to understand with this a very simple example. On the left side, we have 4 data points and our model is very complex. The fitted line is passing through all the data points. Yes, we will get very good predictions for the known data, but when it comes to the unseen data, the model fails to predict. On the other hand, at the right side, the model is simple and very good. It can easily predict the unseen data. This is not complex model. Let's come to the bias and variance trade-off. How we can reduce one and increase the other to get the sweet spot. Along y-axis we have error. Along x-axis at somewhere close to 0, what it called, we have low, and at the other end we have high complexity of the model. The blue curve is actually the total error. The green is the variance, whereas the red is bias. If we move from low to high complexity, we are actually decreasing the bias and increasing the variance. So understanding the bias and variance is critical for understanding the behavior of prediction models. But in general, what we really care about is overall error, not the specific decomposition. The sweet spot for any model is the level of complexity at which the increase in bias is equivalent to the reduction in variance. And we can see the sweet spot somewhere at the middle of high and low model complexity. At its root, dealing with bias and variance is really about dealing with over and underfitting. Bias is reduced and variance is increased in relation to model complexity. As more and more parameters are added to the model, the complexity of the model raises and variance becomes more primary concern, while bias steadily falls. It's very important to know if our model complexity exceeds the sweet spot, we are actually overfitting our model. On the other hand, if the complexity falls short of the sweet spot, we are actually underfitting the model. So it's very important to find out this sweet spot. Unfortunately, there is not an analytical way to find this location. Instead, we must use an accurate measure of prediction error and explore different levels of model complexity, and then choose the complexity level that minimizes the overall error. So, great job guys! We have covered the basics on linear regression and some very important concepts. It's time to learn this widely used technique with more practical examples using data. In the next lecture, we will create our very first linear regression model using Python's machine learning Scikit library. I can't wait to do this. Let's move on to work on our very first machine learning project. See you in the next lecture. Good luck.